Hi, everyone. My name is Inga. I'm a PhD student at McGill University. I am supervised by Prof. Christie Rowe, and my PhD deals with the hanging wall architecture of the Naukluft Nappe complex. I'm going to talk to you today about some deformation-related structures that we mapped and sampled in the hanging wall of the Naukluft. So we know that earthquakes happen on localized brittle faults. With depths, like in this figure from structural geology, brittle failure largely becomes distributed and plastic. Ductile structures are often precursors to brittle deformation, as they often exploit the weaker areas in the crust. Sometimes, though, the opposite effect takes place, and those ductile features become stronger, which prevents localization. That way, rheology, so the strength of the rocks, guides earthquake ruptures. So in my field season in 2019, we mapped both brittle and ductile structures in the hanging wall, and that's what I want to show you today. We study the ductile rocks, the malnites of the Naukluft, to understand their properties and how they facilitate subsequent brittle earthquake-related deformation. By looking at these malnites, we are looking at deformation events that help build the Naukluft Nappe complex prior to its final emplacement. So we're working at the Naukluft. The Naukluft is a thin-skinned foreland trust belt in the southwest of Namibia here. So the Naukluft exposes shallow marine siliciclastic sediments imbricated and folded during the Cambrian in the foreland of the Damara orogeny. So my field area is marked with a blue star over here. It's in the southeastern part of the Naukluft close to the park headquarters. And on the right, you can see the geologic map of the area. So the transfer direction of the whole Nappe complex is northwest to southeast. And each color here represents a different unit cut by black thrust. So the footwall here is in light blue, and all the other colors are the hanging wall structures. The cross section that I'm going to show you right now in the next slide is parallel to this transfer direction. So here you can see the same map on top of the DEM of the area, looking parallel to this transfer direction. And in this schematic cross section on the right, you can see the 5 main structures mapped in the hanging wall, as well as the interpretation of the structures at depths based on cross-cutting relations we saw in the field. So the Naukluft thrust is in the bottom here. It's made up of a fluidized fault rock, the gritty dolomite, and it cross-cuts all the other structures, making it the final deformation feature. Structures A to D are in the order of cross-cutting relations we see in the field. So A, the olive fault cross-cuts the plateau malnite, and D, the Jane fault cross-cuts the Scotty malnite C. So 2 very different malnites were identified here, and in both cases, they're cut by brittle faults, and I'm going to show that to you. Over the next slides, I'll show you both malnites, Scotty and plateau, show you what they look like in the field, in cross-section, in thin section, sorry, discuss how they are similar or different from one another, and what they tell us about the construction of the whole Nappe complex. So the Scotty malnite, which is the upper one in here in the sketch, you can see it here in all its glory, and here you can see my field assistant Julius for scale. This is a 30-meter unit, and this shows us a progressive increase in qualitative shear strain. So I'm going to show you how that looks in thin sections, but notice that in both appearances, you can see layers of purple shale, as well as pink and yellowish carbonatic layers in the malnites. So here on the top, you can see the hand sample cut parallel to the lineation, and in the bottom, you can see the cross-polarized light thin section. So the matrix here is made of interlocking quartz and dolomite in a variety of small grain sizes. This matrix has a shallow dipping fabric of dark bands filled with micas and tiny opaque minerals in here. This is mostly a flattening fabric with some shear along the solution planes right here. This matrix is then cut and shaped into boudins and cut by a set of blue and purple fabrics. These have shear along them as well as flattening. And the blue and purple fabrics are made up of biotite, and they cut through the matrix. And you can see here large-grained carbonate veins and quartz veins that also cut through the matrix. Based on delta clasts, And the kinematics of the boudins, the shear sense here is top to the south-southwest, which corresponds to the transport direction of the whole Nappe complex. Now, zooming in on top here, you can see how the secondary fabrics are shaping boudins here. And in the bottom plane polarized light image, you can see brittle structures that we saw on a smaller scale here. And those brittle structures are accommodating the overall ductile flow of the small net. Another thing you can see here is the white areas that are quartz veins here. And in the top image here, you can see that they cross-cut the fault. So they are older than the fault, and here they are cut by this normal fault. So we also recognize a few generations of vein infiltration here. Okay, so this rock, which is the second appearance of the malnite, consists mainly of a crystalline dolomite matrix with interfingering grain boundaries, and the weak shape elongation fabric that you can see here in pink it's defined by larger grains, with smaller grains more equant and round. Spaced wisps of muscovite are distributed throughout the thin section, and you can see them here, the darker band. Do you see it? And these grains, we think that they have a predominantly detrital origin, and this is supported by their apparently random distribution and consistent grain size. So we also think that they are the remains of the shady layers in the lower strain malnites that we saw before. So the take-home message from this slide is that we have one deformation fabric here that is transposing previous structures, which is normal for highest strained malnites. And there could be previous phases that we just don't see in this malnite. So this is a higher strain malnite, and after staining it, we can say that this is a flow in dolomite, because this is a dolomilnite. Okay, so now we reach the second malnite, the plateau malnite, that is over here. And this is a compositionally and color banded calc malnite with thin discontinuous purple shell layers on a centimeter scale. You can see here the field appearance of this malnite. The exposure of the unit is limited to lenses. You can see that on the sketch. This is the turquoise part here. And the malnitic layers are chaotically folded within these lenses. So here you can see the hand sample on the left, and on the right, this is the thin section of the same sample. First of all, the thin section is split into two main parts, one more rich in clays, and the other one is more rich in carbonate. This goes to show the brittle overprint of these malnites. So we see layers and wisps here of fine-grained opaque minerals that separate a matrix of carbonate and quartz. And we see two different fabrics in each part of the section. After staining, part of the carbonate matrix in the main part of the thin section here is made up of ferric at times twinned calcite. And these are the pink chunks that you see here floating around now. So what we see in this malnite is also ductile deformation events overprinted by brittle deformation. So just to conclude the malnites here, what we see are malnites that show shape preferred orientation. That's why we know that they are malnites. The protolith of toe malnites is pretty similar. It must have been an interbedded carbonate shale sequence, and probably these rocks are mostly derived from the unit which is found in between them, which is the purple shell unit. Over here you can see in the sketch. The malnites show at least three different fabrics, and based on cross-cutting relations, at least two different deformation events. And we do see periods of vein infiltration during deformation, and that might have effect on the strengths of these rocks. And we see both dolomite and calcite that show a malnitic fabric in here. Okay, so to continue with the brittle structures, on the left, what you can see are layers of malnite that are folded and faulted. And on the right, you can see what we suspected to be a breccia of a malnite layer. So basically, this is the chain fault that is over here, the top part one. And what you can see on the micro scale is you're looking at blocks of super fine grade carbonate matrix on a scale of a few micrometers, and each block has a stretching fabric that is in a slightly different orientation. And what separates these blocks is a quartz rich matrix. Based on staining, what we see here is a breccia of a dolomyelonite. So the main point here is that this is the second stage of the story. We see a malonite inside of a brittle fault. And just to close the circle, introduce you to all the structures, this is the olive fault here, and that cross-cuts the plateau malonite. And this is a brittle fault. The fault rock is a breccia here, and it has a damage zone in a scale of a few meters. And yeah, that cross-cuts, the turquoise plateau malonite. So to conclude what we saw, a few ductile and brittle deformation structures were mapped in the hanging wall of the Naukluft. In all cases that we mapped brittle overprinted ductile deformation, interpreting it to be exhumation-related deformation. Now, based on the orientations and cross-cutting relations in the hanging wall structures in the field, what we're seeing is a forward propagating nap stack. So the units at the top or to the northwest are older, and they get younger towards the Naukluft thrust. Based on the ductile flow that we saw in the thin section, sliding on those rocks must have happened under 400 or 500 degrees Celsius, which puts it into the upper green schist facies, well into the earthquake zone. So based on these cross-cutting relations on the fabric that we see in the malonites in thin section, they record at least 2 different ductile deformation events. And to find out more about those, further petrographic analysis is ongoing. Okay, that's what I have for today. Thank you for my thank you to my collaborators. Thank you, Carly, Emily, Julius, and Christie, and thank you all for listening.